All right, good morning, good evening, or good afternoon. Welcome to this video. We're going to be talking about work and energy today. All right, hard work pays off. All right, so we're going to be talking about work as a very specific physics-based quantity here. So when a net force is applied to an object and it accelerates, we know net force is going to generate some acceleration if it's non-zero. But work is going to be a new way of kind of describing what is happening when we accelerate an object. So we're going to jump into this example here of this fella. He's pushing a giant block, and he's exerting a force on it, and then it travels a distance delta x. All right, and we know by the time he gets over here, his speed is going to be non-zero, and let's assume over here the speed is initially 0. All right, so he's accelerating, and he's traveled a certain distance. Well, the work that he has done on the object is defined as the integral of the force vector times the direction vector. dr is the infinitesimal direction, but it's the integral from one location to another. And remember, so this is the dot product of these two things. So for instance, the dot product, as we talked about before, of two vectors gives you a scalar. So the dot product of this force vector and the direction vector is the magnitude of f and the magnitude of the direction times the cosine of the angle between them. And so check out the vector videos that we talked about, particularly the vector multiplication videos. So let's think about if f is constant over this distance, then the work that we've done over this distance is going to be the magnitude of f times the distance that we have moved times the cosine of the angle between things. All right, and so this angle between them, that's going to become important. So for instance, if the force on an object is horizontal and the object moves up, then the angle between the force and the direction in which it moved is 90 degrees, and you guys probably remember cosine of 90 degrees is 0. So that kind of makes sense. Like if a force is acting on an object this way, but it doesn't move anywhere in the direction of the force, it moves 90 degrees to the force, then that force actually hasn't done any work. It's not the one that's actually causing that motion. All right, so it's important to remember that work is a scalar, and it has units. So of force times a distance. So it's newtons times a meter, which gives us units of joules. And 1 joule is 1 Newton meter. So work has the same units as energy. All right, so if we go back to this example of this fella pushing this block along, if he's moving it with some net force, and he moves a distance delta x, and it's moving in the parallel to the direction that the force is being applied, then the cosine of the angle between them is 0. And then the work that it's done is going to be F net times delta x. All right, so we'll come back to work in a moment. Work has the same units of energy, and we're going to talk about types of energy now. So when you apply work to an object, you can increase its energy. And so if an object is moving, it has kinetic energy. So kinetic energy is one kind of energy, which we sometimes write out as Ke. So kinetic energy is equal to 1/2 times the object's mass times its velocity squared. And again, this is a scalar. So you plug in the magnitude of the velocity here. It really doesn't matter what direction it's moving. So in this example 1 here, we have a mass 1 that is moving 3 meters per second in this direction, and a mass 2 that is moving 3 meters per second in this direction. So they're moving in different directions, right? They have different velocities, but they have the same speed, right? And let's say mass 1 is the same as mass 2. They both weigh 2 kilograms. You can calculate their kinetic energies, and they're going to be the same because they have the same speed and they have the same mass. It doesn't matter that they're moving in different directions. They have the same kinetic energy. So you take 3 meters per second squared, times it by the mass, and times it by 1/2, and that's going to give you 9 joules. And the second object has the exact same kinetic energy, 9 joules. Let's think about example 2. Now we have 3 objects. One has a mass of 2 kilograms and a speed of 2 meters per second. Another has a mass of 2 kilograms and a speed of 4 meters per second. So you can plug that in for object 1. You plug in 2 kilograms and 2 meters per second, and you square that and multiply everything. You find object 1 here has a kinetic energy of 4 joules. And if you plug in these numbers here for the kinetic energy of this object, you have 4, and notice that the velocity is being squared. So essentially, what's changed from this scenario to this scenario? The mass has stayed the same, but we've doubled our velocity. So what do you expect is going to happen to the kinetic energy? Well, the kinetic energy is going to be 16 joules. It's going to be 4 times greater because the velocity is squared. So if you double the velocity, you're going to get 4 times as much energy out of it. What about this object? It has a mass of 4 kilograms, so twice as much as example 1, and has the same velocity as this example 1. So we've doubled the mass now compared to this example. And when we double the mass, kinetic energy part 3, the kinetic energy will double, right? But the speed is staying the same. So how are work and kinetic energy related? Well, if work is done on an object, the kinetic energy is going to change. So here we're going to think about the net work. So if you take all of the forces that are potentially doing work on an object and you add them all together, so you think about the net force, we can derive something called the work energy theorem. So if you integrate the work being done from position A to position B, and you think about how the angle is changing between those and what the velocity is at point A and what the velocity is at point B, the work that happens in between point A and point B is going to contribute to changing the kinetic energy of the object. So the net work is going to be over from point A to point B is going to equal the change in kinetic energy from point B to point A. Kinetic energy at point B minus the kinetic energy at point A. So how much kinetic energy do you finish with, and how much kinetic energy did you start with? The change in that is going to be dependent on how much work you did. All right, so one more quantity that we're going to introduce here is called power. All right, so power is the rate at which you are doing work. It's the rate of change of work over time. And so one kind of simple way to explain this is to think about cars. We hear about power and how much horsepower does this car have? How much horsepower does this car have? And generally speaking, the more horsepower you have, the faster you can get from 0 to 60 miles per hour. So let's think about this. Let's say car A has the same mass as car B, Car A, maybe it's a Toyota Camry, and car B is a Porsche or something. Let's say they have the same mass. Car A, the Camry, it can get the 0 to 30 meters per second in 9 seconds. And car B can get from 0 to 30 meters per second in 3 seconds. So the change in kinetic energy between both after they go from 0 to 30 meters per second is the same, right? They both are going to have the same kinetic energy at the same because their mass is the same and their velocity is the same. But car B did the work to get up to that speed 3 times faster. They got there in 3 seconds, whereas car A got there in 9 seconds. So car 2, or car B, has 3 times the power. All right, so we're going to be playing around with these ideas of work and energy and kinetic energy quite a lot. So it's important to get these under your belt, and thanks for listening.